Good morning. My name is Frank Lochel. I'm with CARGILL in the United States. I am a research advisor, and today we're going to be presenting to you some new concepts in some metalworking additives. So, you may not be familiar with CARGILL, but we are the largest privately owned corporation in the world. We are a food producing company. But as part of the food development groups, there are byproducts made when you produce food, like soybean oil or corn oil or wheat. So the group that I represent, we take the byproducts of the food production and we render those into industrial products. They might be lubricants, they might be biopolyols for use in urethane foams. We have additives that we have for bitumen for use in asphalt. We have a special interest in making binders, which are organic resins for use in binders for fiberglass. We also have dust control fluids for fiberglass. So as the world's largest private company, we have the luxury of having 24,000 chemists globally. We'll get all the details worked out. So these are the countries in which we have representation with manufacturing sites. This is the Brazilian manufacturing site in Marinque. So how we got started in looking at the additives that would be of particular interest for metalworking, I took a team of chemists to last year's STLE meeting. It's a group of tribologists that was in Las Vegas last year. We presented some very basic lubricant products, but we also listened to what our customers were looking for. And the main concern was the fact that our Environmental Protection Agency, our regulatory agency, is restricting the use of certain chemicals from the metalworking arena. One of those, as I'm sure you've heard, is the restriction on chlorinated paraffins. Another is a pending regulation to limit the use of biocides. The biocides would be used in either in your formulated product or also as a maintenance item for use at your customers in their coolant sump systems. One of the main concerns that was expressed at this meeting was the fact that many of the coolants that are designed today, of course, contain boundary lubricants, which are, in a general sense, fatty acids that have been neutralized with an alkanolamine. That works well if you use soft water without any kind of cations in it. If you put your coolant into water that has high hardness, in other words, high calcium and magnesium concentrations, you will have a cation exchange between the calcium or magnesium and the alkanolamine that's used to neutralize the fatty acids. What happens then is you start to precipitate the principal lubricant in your product. When you start to precipitate it, you start to blind up your filter papers, and you end up just basically stripping your lubricants out of your product. Also, because you're making a metal grease, all the metal in the area gets very dirty. Your workpieces get dirty, the environment gets dirty. And if you can find a way to keep your lubricant base solubilized in your coolant, you can also maintain the traditional tool life that you design your products to do. So we worked with one of the major coolant suppliers globally and asked them to give us one of their coolants that is most affected when it's put into hard water. We took that coolant and we made gallon jug samples, so 4 liters of diluted coolant at 5%. The reference is on the left there, and that's the one where we made the coolant in hard water. It was about 110 parts per million hardness, approximately equal concentrations of calcium and magnesium. So as I started to say, we made gallon jugs of these materials. The one on the left was just the coolant in hard water. The one in the middle was a gallon jug of the subject coolant at 5% in deionized water at about 12 parts per million. And on the right, we made a gallon jug of the coolant into which we had added 1% of our additive. Then we put it in the hard water. So we let these gallon jugs sit open, and we marked the level so that we could replenish the water back to that level. And over a period of 60 days, the water hardness climbed to 611 parts per million. And that's what you're seeing here. That sensitive coolant in 600 part per million water on the left, the same coolant in deionized water. It didn't change much whatsoever. And then on the far right, you see that same coolant with 1% of our additive at 600 parts per million. We showed these to the supplier of the coolant, and he was really impressed. They pointed out to us that our product with our additive looked better, more transparent than the product in the deionized water. So they're in the process right now of running production trials with this material. I should note that many of these products that I'm introducing, we are just now commercializing. So we're going through patent evaluations. One other comment that I should mention is that CARGILL will supply base oils, so vegetable oils. They could be used as finished products in low-pressure hydraulic systems. But we will never make a formulated product that would compete with any of you. We will be an additive or a base oil supplier. So this product we developed almost by accident. We were making some drilling fluids for use in offshore drilling. The purpose of those fluids is not necessarily lubrication. It has to do more with pressure control. But we looked at that product, and we modified the way we make it, and then we evaluated it as a lubricant. It is not subject to hydrolysis like any ester would be that's placed into water. It's 100% water soluble. It has a molecular weight about 5,000. It is not subject to hydrolysis. The product that we currently have does tend to foam. So we're working to reformulate that in the synthesis process so that we eliminate the tendency for it to foam. Because it does foam, we're now presenting this as an additive that you can use to decrease the coefficient of friction in your existing coolants that have defoamers. But within 60 days, we will have a product that will have the same performance products, but without the foam. Once we have that, then our product could be a standalone synthetic coolant. To define a synthetic coolant, for those who might not be aware, they have the other name of chemical solutions. So every additive you put into your product has to be water soluble. They're very, very difficult to make, and they sell to the end user for about $11 US per kilogram. That's the final price for the finished fluids. The problem that is experienced with synthetic coolants is what we call selective depletion. So you have multiple additives, all water soluble, but some have a much higher affinity to a metal surface. So those materials get taken out of your coolant, and the performance of your coolant degrades over time. With this product, it's a single component, so you cannot have selective depletion. We have some performance data we can show you. The piece of equipment we have in our laboratory is a simple 4-ball machine. So we started just looking at what the coefficient of friction would be. And at 100%, we have seen measurements for coefficient of friction as low as 0.027, but we're reporting 0.037. That's the highest we ever measured. That's at 100% active, and the scar was 0.033 centimeters. We diluted it to 5% in hard water, and of course the coefficient of friction went up, but it's for a standalone product with no additives, that's still not too bad. And the scar went up appreciably to 0.08 centimeters. We then took that product and sent it to an independent testing laboratory where they compared it with what they consider a recognized standard for a synthetic coolant in the United States. We don't know what exactly they used, but we believe that they knew what they were doing when they used that as a reference. The supplier of that product recommends it to be used at 8%. So the test was run on 6061 aluminum with a 6M form tap. Now, if you're familiar with micro tap testing, there's two types of tools you can use. One is a cut tap, which actually removes the metal as it forms a thread. The other is a form tap, which is much more difficult. It's not a cutting operation, it's an extrusion process. So the heat generated and the torque generated are much, much higher. So you can see with the recognized reference, they had 364 Newton centimeters of torque required to form a hole of a certain depth. We ran our product at 5% and at 10%, and even at 5%, we were lower in total torque numbers than the reference. So at this point, this product is now being commercially evaluated by several major lubricant suppliers. Another subject that was of great interest in the United States is the fact that the EPA has put a deadline on the use of mid-chain chlorinated paraffins. That deadline was last June, a year ago. Because no one had a proper replacement product, the EPA backed off, and they're going to set a new deadline. We thought with our typical chemistry we use in CARGILL that this would be quite a challenge. I mean, there's a number of companies that are far, far more competent, I think, in coming up with a chlorinated paraffin offset, but we got lucky, I believe. So what we have is an additive that we can make very inexpensively, very quickly, and it is free of all chlorine, sulfur, and phosphorus. Again, we used the equipment we had in our laboratory, which was the 4-ball, but we ran it as an EP test. In an EP test, you're looking at the first seizure load, and then you look at the weld load. So we used a mid-chain chlorinated paraffin, which as a standalone additive contains 56% chlorine. Our product, of course, has no chlorine, sulfur, phosphorus. We ran them both at 5% in oil. It was a vegetable oil. And we were surprised to see that the initial seizure load was equal at 80 kilograms. We continued the test to the failure, which is the total weld load, and not surprisingly, we got beat on that one. We do have some additional data, which is microtap data, but the slide didn't get added into the presentation. So you'll have to take my word for this one, but we took the same products, ran these on microtap at 5 and 10% of each of the additives. On steel, at 5 and 10%, both additives, the chlorinated paraffin and the CARGILL additive, were identical in torque, which we were quite surprised about. On aluminum, we actually, at both 5 and 10%, were far superior to the chlorinated paraffin. I attribute that to the fact that to activate a chlorinated paraffin in the extreme pressure regime of lubrication requires a lot of heat, so it has a very high activation temperature. What we learned is that our product has a much lower activation temperature. So we're seeing our product now to be both an anti-wear and an extreme pressure additive. Oops. Okay, I hit the wrong button. Help. The other concern that I mentioned is the EPA, the Environmental Protection Agency in the United States, intends to eliminate the use of biocides. As formulators of coolants, you probably add biocides to your formulations. And then as a maintenance item with your customers, you probably add tank-side biocides. That is not going to be allowed in the near future in the United States. So we're working with one of the major coolant suppliers, and they are very advanced in being very close to having a totally bioresistant fluid. They asked us if we could assist, so we have actually begun development of this product. We haven't done very much because of time limitations, but we do know the product will be 55 centistokes at 20 centigrade, and the density is 1.28. So we're seeing this product to be, we'll call it biostatic. We're never going to claim that it's a biocide. It may have some tendencies to be biocidal, but it's just not going to be a food source for bacteria and yeast and mold. So we're pretty excited about this one also. Then the last subject we'll talk about is esters. Everyone knows trimethylpropane trioleate is an ISO 46 viscosity grade base oil, typically used in hydraulic systems with several different additives to improve oxidation stability and corrosion principally. So we actually have an ISO 46 that we designed specifically for marine applications. What makes it different is a typical TMPTO, if it leaked out of an underwater hydraulic system, would float to the surface and cause a sheen, so a rainbow effect on the surface of the water. On offshore drilling rigs, there are EPA helicopters flying around looking for sheen, and if they see a sheen on the water near the drilling rig, they will impose a significant fine. For every day they see that sheen, it's tens of thousands of dollars in penalties. So the advantage of our TMPTO for marine application is it will not sheen. We also thought, thinking more from the commercial side, that if we could come up with two products, say an ISO 68 and an ISO 680, all made with the same polyol, but with different acids, we could save a company a lot of money by having not to inventory all the different ISO viscosity grades. So if you were to buy from us an ISO 68 and an ISO 680, you could blend those to any intermediate ISO viscosity grade without fear of transesterification that would change the properties of the base esters. So we do have those on offer, and we also have, again, typically for the marine industry, they have a demand for an ISO 220 and an ISO 460. But for those, they do not want synthetic esters. They want biorenewable esters that would be easily biodegraded in an aqueous system. So we do have those also available. I think we've talked about this already. So as a summation, as we talked about, Cargill will never compete with you with your final customer, the metalworking customer. But we will work with you to help you develop formulas with our additives to have the best possible products available for your customers. And our local distributor is Univar, and they have a booth here, so we can be available there to answer questions. But if there are questions now, I'd be happy to try to understand them. All right, well, thank you very much, and we can see you at the Univar booth. Thank you.